Deep beneath the tallest building on Earth is an electrical system that most visitors will never know exists. It does not power the high-speed elevators. It does not illuminate the world-famous observation decks. It exists exclusively to help protect the massive steel skeleton buried inside the foundation from a silent and relentless chemical threat. Above ground, the towers of Dubai are fighting a visible war against extreme heat and desert winds. Below ground, they are part of an electrochemical circuit that never truly switches off. Groundwater at the site of the Burj Khalifa was documented to contain chloride levels up to 4.5% and sulfate levels up to 0.6%. Engineers officially described this submerged environment as extremely corrosive. To combat this, a highly sophisticated cathodic protection system using titanium mesh was integrated directly beneath the foundation mat. This raises a terrifying question for the future of the city. Why would a concrete foundation need an active supply of electricity to survive? To understand the true vulnerability hiding behind the endless wealth of Dubai, we have to stop looking at the glittering skyline. We must descend 50 meters beneath the surface to witness a war that the city can never afford to lose. Most people imagine the foundation of a super-tall skyscraper as a single, indestructible block of solid concrete. When you look at the promotional videos of Dubai, the city sells an image of absolute permanence and total dominance over nature. The reality of the engineering tells a much more complicated and expensive story. The Burj Khalifa does not rest on a simple flat slab. It is supported by a massive concrete mat that is nearly 3.7 meters thick. Beneath this enormous mat, engineers installed 194 board piles deep into the earth. Stand beside just one of these concrete piles, and it is wider than a tall human being. Each pile descends approximately 43 meters into the ground, relying heavily on friction with the surrounding calciciltite and conglomeratic layers to hold the tower in place. During the testing phase, a single test pile successfully withstood a load of over 6,000 tons. The sheer scale of this subterranean fortress is breathtaking. What surprised me the most is not the physical size of the foundation, but the fact that it was deliberately placed inside a geological environment that actively wants to tear it apart. The groundwater beneath the glamorous downtown district is highly aggressive. It is heavily saturated with corrosive ions that exceed the concentrations typically found in standard seawater. This geological reality completely shatters the illusion that Dubai simply conquered the desert. The city placed its most valuable and iconic asset directly into a microscopic battlefield. Building massive concrete pillars is only the first step of the process. The real challenge is keeping those pillars intact over decades of constant exposure to toxic groundwater. Physical size alone is not a true defense mechanism, because concrete is not the impenetrable solid wall that it appears to be to the naked eye. From the outside, a concrete pillar looks like a flawless fortress wall holding up the sky. Under a powerful microscope, it looks much more like a densely populated city of intersecting tunnels and hollow caves. Concrete is fundamentally a porous and multi-phase material. Within the hardened cement paste, there is a complex network of capillary pores, microscopic voids, and tiny internal fissures. The American Concrete Institute defines permeability as the ease with which liquids or gases can travel through a substance. They explicitly note that water and aggressive chemical ions can easily navigate through the pore system of concrete. If tiny shrinkage cracks develop during the curing process, they essentially become high-speed highways for these external threats. This means the danger to the foundation does not come from rushing water smashing against the concrete like a tidal wave. The true danger is that the aggressive groundwater only needs to keep moving slowly through pathways that are far too small for the human eye to see. As the water infiltrates the structure, it carries dissolved ions with it. This process is known as diffusion, where ions move from an area of high concentration in the groundwater to an area of low concentration deep inside the foundation. The city of Dubai spends billions of dollars marketing its perfect, pristine exterior to international tourists. Yet beneath the luxury hotels and record-breaking shopping malls, millions of gallons of groundwater are constantly pressing against the porous concrete of the entire city. Every passing second, water molecules are slowly inching deeper into the microscopic tunnels of the foundations. Of all the invisible invaders moving through the dark underground, chloride is the single element that the buried steel skeleton has the most reason to fear. To understand why chloride is so devastating, we must first understand why steel can survive inside concrete at all. Under normal circumstances, the highly alkaline environment inside healthy concrete acts as a chemical guardian for the reinforcing steel. This high alkalinity naturally creates a microscopic, invisible, passive oxide film on the surface of the metal. As long as this passive film remains intact, the rate of corrosion is kept incredibly low, allowing buildings to stand safely for decades. However, this peaceful state is exactly what the chloride ions are designed to destroy. When the groundwater carries enough chloride deep enough to reach the steel reinforcement, the chemical balance violently changes. Once the chloride concentration hits a critical threshold at the surface of the steel, it locally breaks down that protective passive film. This is the precise moment the corrosion process is initiated. A microscopic electrochemical battery is suddenly formed inside the damp concrete. One specific area of the steel begins acting as an anode, which means it starts actively dissolving and losing pure metal. Another nearby area acts as a cathode, facilitating a completely different chemical reaction. The moisture trapped inside the microscopic pores of the concrete serves as the perfect electrolyte to keep this destructive circuit running. As the steel dissolves, it creates corrosion products, which we commonly call rust. The terrifying part of this chemical reaction is that rust occupies a significantly larger volume than the original steel. As the rust continuously accumulates along the boundary between the metal and the concrete, it generates a massive amount of outward pressure. This incredible internal pressure eventually overcomes the tensile strength of the concrete itself. The concrete begins to crack from the inside out, exposing even more steel to the aggressive groundwater, and eventually causing large chunks of the protective cover to completely fall off. The Federal Highway Administration notes that this initiation phase often takes up the longest portion of a structure's service life. This means the durability clock is already quietly running long before the first visible crack ever appears on the surface. This is what makes the threat so deceptive and dangerous for a city completely reliant on its architectural image. The concrete can still look entirely calm and structurally sound to a building inspector, while the chemistry at the steel surface has already permanently changed. The structural integrity of a building might be compromised in the dark, years before any alarms are sounded. But this is where most explanations, including many dramatic videos found online, make a crucial technical mistake. Chloride-induced corrosion is not the same thing as giant salt crystals physically exploding inside the concrete. There is more than one chemical enemy lurking underground, and they do not attack the foundations in the same way. The reality of the underground war is far less cinematic than giant glowing crystals physically tearing a skyscraper apart. However, the scientific truth is actually far more interesting and much harder to manage. The engineers in Dubai are not just fighting a single enemy. They are fighting multiple transport and chemical reaction mechanisms simultaneously, each requiring a completely different defense strategy. We can separate these threats into three distinct categories of destruction. The first mechanism is the chloride-induced corrosion we just explored. Its primary target is always the reinforcing steel, and its ultimate results are internal rust, severe cracking, and the violent spalling of concrete. The second mechanism is known as chemical sulfate attack. Unlike chloride, sulfate does not care about the steel reinforcement at all. Its primary target is the actual chemical composition of the cement paste itself. When sulfates penetrate the concrete, they react with the internal compounds to form new, expansive minerals. The American Concrete Institute emphasizes that sulfate attack is an incredibly complex process that can manifest as severe expansion, deep cracking, dangerous softening, or the total deterioration of the material. The third mechanism is physical salt attack, which is frequently misunderstood. This occurs when water-carrying dissolved salts enters a porous material and then evaporates. As the water turns to vapor, the remaining salt solution becomes supersaturated, forcing crystals to grow rapidly just beneath the surface of the concrete. The pressure from this rapid crystallization can cause the outer surface to heavily flake and peel away. However, this specific weathering phenomenon is mostly restricted to evaporative zones or surfaces experiencing constant wet and dry cycles. It is not the primary mechanism destroying deeply submerged foundations that remain constantly underwater. The danger for Dubai is that a single drop of groundwater can contain the ingredients for all of these attacks at once. The city is built on a geological cocktail of chlorides, sulfates, and other aggressive salts. Once the structural engineers accurately separated these distinct threats, they could finally begin to build a defense. But they quickly realized there was no single miracle material capable of stopping all of them simultaneously. There is a widespread misconception that you can simply order a batch of salt-proof concrete and completely ignore the groundwater problem. In the construction industry, engineers do utilize sulfate-resisting cement to help mitigate specific chemical reactions. This specialized cement significantly reduces the susceptibility of the concrete to certain types of severe sulfate attack. But using this cement does not magically stop chloride corrosion. It does not prevent water permeability. It does not heal microscopic shrinkage cracks, and it offers no absolute immunity against physical salt crystallization. Calling one specific type of cement completely salt-proof would be like calling one heavy padlock a complete home security system. It might successfully stop one specific method of forced entry, but it does not seal every open window, reinforce the weak walls, or guard the underground tunnels. Achieving true structural durability in an environment like Dubai requires a massive, integrated system of defenses. It relies heavily on the precise selection of materials, meticulous geometric design, the thickness of the protective cover, and aggressive crack control. It also requires absolutely flawless construction quality, which is incredibly difficult to guarantee when thousands of laborers are pouring thousands of tons of concrete in the blistering desert heat. The engineers responsible for the Burj Khalifa understood that they could not rely on a single wall to hold back the ocean of chemicals beneath them. They knew that any single point of failure could eventually compromise the most famous building in the Middle East. Therefore, they did not just build a foundation, they built a highly complex defense, in depth, consisting of 6 distinct layers of protection. Each layer of defense beneath the Burj Khalifa functions like a heavy vault door closing in the face of the encroaching groundwater. The first layer is a specialized waterproofing membrane system. The primary goal here is to physically limit the direct contact between the concrete and the water. However, no waterproofing membrane in the world is absolutely perfect over the lifespan of a building. Seams, edges, installation defects, and structural penetrations always provide a microscopic opportunity for water to eventually breach the first wall. The second layer of defense is the extremely dense, low-permeability concrete itself. The pile foundation utilizes a high-strength 60 megapascal mixture containing approximately 25% fly ash and 7% silica fume. It was carefully designed with a very low water-to-cement ratio of just 0.32. The goal was not to make the concrete mathematically impermeable, because that is impossible. The actual goal was to make every possible microscopic route taken by the groundwater significantly longer, much narrower, and far more difficult to traverse. The third layer is a substantially thicker concrete cover. By deliberately increasing the physical distance between the outer soil and the inner steel, the engineers drastically increased the travel time for the invading ions. The fourth layer involves specialized corrosion inhibitors. These chemical additives were carefully mixed directly into the concrete to help slow down the inevitable electrochemical reactions once the chlorides finally arrive. The fifth layer is rigorous thermal and crack control. Because the foundation mat is nearly 3.7 meters thick, pouring the concrete generates a massive amount of internal heat. If the concrete cools too quickly or unevenly, it will instantly crack, providing a high-speed bypass for the groundwater. The engineers had to conduct massive trial pours and utilize chilled water just to manage the thermal curing process. The sixth layer is the use of a controlled permeability formwork liner. This special liner was applied to the foundation mat to create a dense, highly resistant outer skin of concrete that further slows the penetration of chemicals. Every time the water breaches one layer, the speed of the chemical invasion drops, but it never completely stops. Despite this incredible fortress of chemistry and geometry, the designers knew it was still not enough for a structure designed to break global records. They still chose to add one final defense mechanism, a defense that does not merely slow down the water, but one that actively interferes with the fundamental electrical reaction of the corrosion itself. The final layer of protection is where the engineering of the Burj Khalifa shifts from a passive shield into an active, energy-consuming weapon. As we established earlier, the corrosion of reinforcing steel is fundamentally an electrochemical process. When the passive film breaks down, electrons flow through the steel from the dissolving anode to the protected cathode, while ions travel through the moisture in the concrete. To stop this naturally occurring battery from destroying the foundation, the engineers utilized a technology called impressed current cathodic protection. The concept is incredibly brilliant. If corrosion is essentially an unwanted electrical current generated inside a gigantic wet battery, you can stop it by introducing a stronger, controlled current moving in the exact opposite direction. By applying a continuous direct current from an external power supply, the system artificially forces the entire steel reinforcement structure to act as a cathode. When the steel is held in this cathodic state, the destructive anodic reactions are suppressed, making it virtually impossible for the metal to dissolve and turn into rust. Official engineering documents confirm that an impressed current cathodic protection system, utilizing a highly durable titanium mesh, was installed beneath the foundation mat of the Burj Khalifa. This titanium mesh functions as the permanent anode for the artificial circuit, distributing the protective electrical current evenly across the massive steel skeleton. However, there are several dangerous misunderstandings about how this technology actually works. First, this electrical current does not magically neutralize the salt water or remove the chlorides from the earth. The toxic chemicals are still there, waiting for the power to fail. Second, the system is not designed to charge the foundation like a battery. It is an active regulatory system meant to strictly control the electrochemical state of the metal. The Federal Highway Administration notes that while titanium mesh anodes are incredibly effective in chloride-contaminated environments, the associated rectifiers, continuous wiring, and electrical components must be rigorously maintained. This means the tallest building on Earth does not just stand on concrete and steel alone. It stands on a deliberately engineered electrical environment that must be constantly monitored, verified, and powered. This is a profound realization that changes the very definition of architectural permanence. A traditional monument built of solid stone can simply exist in silence for centuries. An engineered defense system like the one beneath Dubai must remain an active, fully funded, and constantly maintained operation. If the city ever loses the ability to monitor and fund the protection of its infrastructure, the desert will immediately resume its slow, chemical dismantling of the foundations. This brings us to the most critical and often ignored vulnerability of the entire Dubai economic model. The true cost of survival is not just the price of the concrete. It is the relentless, never-ending economic burden of fighting the environment. This is the part of the Dubai narrative that is the most fascinating and perhaps the most fragile. The glittering skyline looks incredibly permanent because all of the exhausting work required to preserve that permanence has been deliberately hidden from the public eye. The engineering marvel beneath the Burj Khalifa is an extreme case of survival, but it perfectly reflects the broader economic reality of the entire city. Dubai has built its entire global identity on being an unstoppable machine of luxury, tourism, and real estate. Recently, the city proudly announced that it welcomed over 17 million international overnight visitors in a single year. On paper, these record-breaking numbers sound like absolute proof of an invincible economy. But record airport traffic and crowded shopping malls do not erase the silent, compounding costs hiding beneath the surface. The hospitality sector is currently facing immense pressure from rapidly expanding regional competitors. As neighboring countries aggressively pivot towards international tourism, Dubai must constantly build newer, larger, and more extravagant attractions just to maintain its market share. This creates a dangerous cycle of endless real estate development. Investors are continually pouring money into new luxury towers, expanding the skyline further into the harsh desert and deeper into the aggressive groundwater. But every new tower built in this environment requires the same expensive, rigorous durability strategies to survive. The cost of waterproofing, the cost of specialized concrete, and the cost of continuous electrochemical protection are massive. These are not one-time expenses. They are permanent operational burdens that rely entirely on the assumption that hotel occupancies will remain high, property values will always rise, and foreign capital will never stop flowing. What happens when the revenue per available room begins to stagnate due to regional instability or a global economic slowdown? What happens to a city when the rapid expansion of real estate outpaces the actual population growth, leading to an oversupply of luxury properties? The buildings cannot simply be abandoned or left unmaintained. The groundwater does not care about hotel occupancy rates or the shifting dynamics of global aviation. If the revenue streams weaken, the cost of keeping the invisible chemical war at bay becomes a heavy anchor on the economy. The buildings in Dubai are essentially high-tech machines, and machines are expensive to run. They require massive amounts of desalinated water, incredible amounts of electricity for air conditioning, and continuous technical intervention to stop the geology from reclaiming the land. When you look at the breathtaking skyline of Dubai, do you see a collection of monuments that have successfully defeated the harsh desert environment? Or do you see a network of highly vulnerable machines that must constantly negotiate with an environment that wants them gone? The Burj Khalifa is routinely presented in marketing campaigns as the ultimate proof that Dubai has conquered nature. Its foundation tells a significantly more complicated and sobering story about the limits of human ambition. The super-tall tower survives not because the concrete is magically immune to the aggressive salts of the earth. It survives because the structural engineers took the threat of the underground environment seriously enough to build 6 separate doors against it. They had to redesign the chemical makeup of the concrete, dramatically increase the physical barriers, and even introduce a permanent supply of electricity just to control the microscopic chemistry within the steel. This level of extreme engineering reveals the true vulnerability of the entire regional economic model. The extreme wealth generated by tourism, aviation, and luxury real estate is not just being used to build the future. A massive portion of it is being quietly spent simply to prevent the environment from erasing the present. As long as the tourists keep arriving and the global capital keeps flowing, the city can afford to keep the electrical shields running and the water out. But a monument that requires active daily intervention to survive is not truly permanent. Dubai did not defeat its geology. It simply bought a highly engineered, incredibly expensive truce with it. Which is more impressive to you? The record-breaking height of the Burj Khalifa in the sky, or the invisible, active engineering required to protect everything that lies below it? Let me know your thoughts on the true cost of architectural ambition in the comments below. If you value investigative documentaries that look beyond the glossy brochures and uncover the hidden systems keeping modern cities alive, please subscribe to the channel. The next major warning sign is rarely where the official marketing tells you to look. This video explores documented engineering protection systems and broad economic pressures. It does not claim that the Burj Khalifa is currently structurally unsafe or that a collapse is imminent. Groundwater chemistry, structural designs, and real estate dynamics vary heavily across different sites. This analysis is based on available engineering literature and public economic data, and is not intended as financial, investment, or travel advice.